Good morning. My name is Dwayne Davis. I'd like to welcome everyone today to our webinar. It's Hipot Testing Basics, Part 2. It's understanding the features of your Hipot tester. Last week we did Part 1, which talked about some of the Hipot tests and what some of the tests are and how they're done. Today we're going to cover a little bit more about some of the features that the equipment have on them today and what advantages that actually gives you. But before we get into that, I wanted to go over a few meeting notes. As we go through the material today, if you have questions regarding the material being presented, please address those to Saeed over our Q&A facility, and he will do his best to try to answer those questions as we go through the material, or he can interrupt me as we go through the material if it's something that we're presently covering, and we'll talk about it a little bit. If there is stuff that we are not able to get to, we will respond to your questions, privately after the webinar is complete, this kind of stuff. If you have problems with the audio or visual presentation, please address those to Rebecca through our chat line, and she will do her best to try to get those resolved so we can get you back to where you're able to view the webinar or hear the material being presented and stuff here. Okay. If you would like a copy of this presentation, you can send an email to Rebecca at the email address shown here, and she will send that out to you via email. With that, we'll go ahead and get started. Again, my name is Dwayne Davis. I am Tech Support Manager for Associated Research, and I've been here now about 44 years. So, as we go through this material, I will do my best to try to, answer any questions and stuff that you may have regarding Hipot testing and stuff. I want to go over the outline first. Our webinar is understanding the features of your Hipot. We're going to talk a little bit about some of the older technology, and then we're going to get into AC versus DC testing, the limit settings you have on your tester. Today we use high and low limits. We also have some features called charge low and ramp high, and we're going to talk a little bit about what those do for you in your testing process, why you might want to set both high and low limits. The testers today typically use multiple fault detection systems for shutting down the Hipot tester, and they monitor different things. We have some that actually monitor high-frequency noise that is generated due to an arcing condition. Again, we have both the high and low-limit detectors. We have high-speed shutdown detectors that are essentially set at the maximum capacity of the instrument. We have GFI detectors. So there's a lot of different detection circuits, and we're going to talk about what those do for us and what kind of advantages and stuff that gives you as far as interpreting what's actually going on during the testing and stuff also. Line and load line and load regulation. What is it and why is it used? Why is it necessary? What advantages does that offer you? Again, smart GFI, what is that? Ground continuity function. This is built into most of our Hipot testers today that allows you to perform a continuity of the ground conductor of your product during a Hipot test. So it's both a time-saving device as well as performs a second functional safety test that is required as a 100% routine production line test if you are testing a Class 1 product. And we'll also talk about the PLC controls on capabilities of your Hipot testers and stuff, that you know, what advantages and stuff that also offers. Okay, again, quick review. What is a Hipot test? Dielectric voltage withstand test, or Hipot, which is an acronym for high potential test, is a test that is actually designed to stress the insulation far beyond what it will normally encounter during the normal life cycle of the product itself. It's assumed that if the insulation in the product that you're manufacturing can withstand this much higher test potential for a given period of time, it will adequately function normally throughout the life cycle of the product. And this is kind of where the term voltage withstand test comes from. But, this is a Hipot test. One that is routine Hipot is what we're going to be talking about mainly today. This is something that is done on a 100% level on the products that you manufacture. Testers today versus older technology, equipment that was made 15, 20 years ago, 25 years ago. If you're an old timer like me, that we're using stuff that was made back in the 1960 era. A lot of the stuff had analog meters. The analog meters, one of the difficulties with those, they had a slow response time. Typical response time of an analog meter was anywhere from 2 to 3 seconds. And this is how long it took for the meter to actually stabilize on a reading if you basically just activated a test where you had your voltage preset for a particular value. Just initiating that test, it took anywhere from 2 to 3 seconds for that meter to settle in on a reading where you knew for a fact that you were reading approximately what the test voltage was that you had it set for. Accuracy on a lot of the old analog meters, again, typical accuracy was anywhere from 2 to 3% of the full scale value. What do you mean by full scale? Well, on if your instrument is capable of producing 5,000 volts and you had a 3% accuracy, which was typical for an AC Hipot tester, you were talking about 3% of 5,000 volts. So that was anywhere across the display. So if you're looking at a 5,000 volt reading, then let me run through this real quick. Sorry about that. So 5,000 volts and times 3, percent. Back up. 0.03. Okay, was 150 volts. So, anywhere along that scale, you're talking about, my accuracy could be plus or minus 150 volts of that reading. So if you're testing at 1,000 volts, that's really over a 10% error that could occur at that setting. So, rather than a 1% or 2% of reading that is typically done now with a digital instrument, your accuracy is much, much worse with, an old analog meter that have, these type of accuracies and stuff here. Again, the older instruments typically had manual adjustments. So, you were looking at a variable transformer that was used to adjust the output voltage. The regulation of the equipment itself was really dependent upon the VA rating of the tester itself. Many of the standards specify yet today that you have to use a 500 VA rated Hipot tester to perform some of these tests. And the reason for that was to make sure that the voltage did not sag during the testing process, that the Hipot had the capacity to be able to supply the voltage and not waver under varying load conditions. So they specified a high current capacity to be able to go through and perform the test. What problems does this create? Using a high current capacity instrument creates a little bit more of a hazard to the operator. If you think about it, if you got a 5,000 volt, 500 VA rated tester, that instrument is capable of producing 100 milliamps of output current under a full load current condition. So the short circuit current of that instrument is specified typically as 200 milliamp short circuit, and most testers are able to supply much, much more than that under a short circuit condition and stuff there. So it creates a hazard to the operator. If the operator makes a mistake, it could be lethal. So, some of the older testers, or even some of the standards that require a 500 VA rated tester, is rather questionable in regards to safety of the operator. If the instrument that you're using, if the Hipot has a regulated output, then you can get by with a tester that's a much lower current capacity, provided it's got the current capacity to be able to test your product. Okay, but in a lot of cases, you're talking about testing a product that draws only a few milliamps of current, and if that's the case, then why do you need something that's capable of supplying 100 milliamps, if you can do something where, you're supplying a tester with 20 milliamps? It's a lot safer for the operator. Okay. Limited information on a failure condition. Again, older testers had, in many cases, you maybe had just a kilovolt meter. You might have had a leakage and a breakdown light that lit up to indicate a failure. Some units had current meters, some did not. So, it really required close attention of the operator to know why your product failed. Today, with the newer microprocessor technology, you can look upon the display of the instrument and it will tell you you had a high limit failure, you had a low limit failure, you had a continuity failure, it failed due to an arcing condition, it was a short, so all this information can be obtained with testers today that have multiple failure detection networks. depending upon which one picks up the failure, it feeds that information into the CPU, and the display indicates the failure condition that has occurred during the testing of your product. Again, digital metering, again, much faster response time, better reading resolution, higher accuracy, typically 1 to 2% of reading, not a full scale. So, you know, this gives you a much tighter accuracy and stuff. One of the things that I've seen in a lot of the specifications in regards to the calibration of your equipment. Again, a lot of the safety agencies now require that your Hipot tester or your test equipment in general be calibrated by an accredited calibration laboratory. And they may require 17025 or Z540 accreditation, or even a CTL accreditation. One of the things with CTL accreditation, they still go based upon accuracies of full scale. So actually, the accuracy of the equipment on some of the lower voltage readings and stuff and lower current readings is not as good or is a much looser spec in regards to the accuracy of the equipment with a CTL certification than a 17025 accredited cal or a Z540. Okay. Regulated output. Instruments today are equipped with line and load regulation to actually maintain the output voltage under varying line and load conditions. And this basically reduces the need for testers that have such a large output current capacity on the transformers. If they are capable of maintaining the output voltage during the test through the use of feedback circuits, it does provide a higher degree of safety also for the operator. If you don't require such a brute force Hipot tester that could create a much larger shock hazard to the operator if they do make a mistake and somehow get shocked during the testing process. Today, with microprocessor technologies, it allows for setting up of test parameters. You can do that without having high voltage on. You can set multiple memories for different test programs if you're testing different products. You can link tests together, do multi-function test or using switch matrix scanners, test multiple points or multiple products, at the same time or in sequence. And your memories can be stored into onto an EEPROM within the instrument and recall basically at the touch of a button. Or you can use a computer to actually store all your test data and maybe even utilize a barcode scanner, scan in the serial number or model number of the equipment being tested, and have it automatically load the test program that you're running for that particular application. So microprocessor technology has come a long way and makes it much simpler to set up test and have your testing done much more consistently. Okay. Let's talk a little bit about AC versus DC testing. Whenever you're doing a Hipot test, if you're doing an AC test, some advantages that it offers is that many times the test can be done quicker. You don't have to ramp up the voltage, so the voltage can be applied instantly. So if you're doing a routine production line test and I am trying to shave as much time off the testing function. Doing an AC test is, in many cases, a much faster test than if I have to do a DC test, especially if my product is, requires a longer ramp time or stabilization time or something. If I'm just trying to read, some low leakage current levels and stuff. So in doing an AC test, I don't have to ramp up the voltage. I can apply it instantaneously, so the test can be done in a shorter time span. Doing AC testing, if my product is still connected at the end of the test, okay, I don't have to worry about discharging the product, because the product will discharge back through the impedance of the output transformer of the instrument. The transformer is still, connected to the device under test. At the end of the test, voltage is shut off on the primary side of the transformer, and the device under test will discharge back through the secondary of the transformer, and I don't have to worry about discharging it. Again, that is provided that the product is still connected at the end of the test. If you're doing what we call hot testing, where the probes are energized and you're moving from one component to another component just as fast as you can, energizing it, and then pulling the probe off while the Hipot is still on, then you may have to worry about the product holding a charge. Because if you remove that probe at the peak of the sine wave, that product will still be charged and could represent a shock hazard to the operator or the next person that comes in contact with that device. Okay. In doing AC testing, you are testing both polarities during your test cycle. It is switching polarity going positive and then going negative 60 times a second, or whatever your frequency is. So it's changing polarity constantly. Why is that important? Some products are, or some insulation may be polarity sensitive. So this may be a more stringent test doing an AC test than a DC test. Okay. AC disadvantages, you are measuring total current, which is a combination of reactive and resistive. This can be both an advantage and a disadvantage. From a shock hazard standpoint, I am interested in the total current, okay? Which is a combination, again, of reactive and resistive. If I'm more worried about from an insulation standpoint, then I would be more interested in what the current is due to the resistive element of the product. There are products or Hipot testers that can measure both the real and total current. They are a little bit more expensive. Being able to to have that capability of monitoring both of these requires some special circuitry and stuff involved. Okay. In doing AC testing, it requires a Hipot tester that is larger in current capacity, because you have to worry about the distributed capacitance of the product. Everything that you test is a capacitor. You are testing the insulation between two current carrying conductors. That is a capacitor. When you tie the hot and neutral conductors together, you are testing the insulation between those conductors and any exposed dead metal, which is a capacitor. The more capacitance you have, the higher the leakage current, the higher the current capacity of the tester is required to be able to go through and do that test. Okay. So if you are doing AC testing, you may need a tester with a higher current capacity. Again, depends upon your product itself. DC has some advantages. One is that you are observing the current that is due to the resistive element, so you are seeing what the real current is that is a direct result of the insulation resistance of the product. The size of the tester can be smaller when you're doing DC testing because if you ramp up the voltage slowly, it doesn't need a huge transformer or a large current capacity. You can bring up the voltage slowly and allow for that capacitance of your product to charge up. Therefore, your tester is a little safer, but you still have to worry about the charge on that capacitive load within your product itself. Everything that you test is a capacitor. A capacitor is a storage device. So you have to worry about discharging the item at the end of the test. Okay. Most of the testers today have an output shorting device built into them. Check the specifications on your product to make sure. But one thing to keep in mind, the product must still be connected to the Hipot at the end of the test in order for that output shorting circuit to work. If you have an open circuit, the part will not be discharged. You have to have that discharge path in order to discharge the item. If you have an open test lead, it is possible that you may be able to charge the device but not discharge it, depending upon voltage being applied. It may jump the gap to charge the device but not jump the gap to fully discharge it. In doing DC testing, typically you have to ramp up the voltage to allow for the capacitance of your product to charge up. And that ramp time is a function of whatever your test voltage is, your trip setting, the capacitance of the item that you're testing. So that's kind of an experiment in how long of a ramp time do you actually need based upon the product that you're testing. One disadvantage, it is only stressing the insulation in one polarity. Some type of insulating material is polarity sensitive. You typically have to test at a higher test potential. The multiplier for an equivalent test is not always consistent. But if you are doing a DC test, typically the DC value is at a minimum 1.414 times the AC test potential in order to get a adequate or equivalent test potential being applied to the product. DC is not always accepted by all testing agencies. So again, check with your testing agency to see if you can do a DC test in place of an AC or vice versa. Some standards will typically request that you test at the same type of supply that is being used to power up your product. If your product is being powered from an AC source, they may want you to test it with an AC source. If it's being done at 50 hertz or 60 hertz, you may have to test at that frequency. Some say do it under the worst case condition, which would be the higher frequency level, because that would create more leakage current, okay, due to the capacitive reactance of the product that you're testing. Okay. And again, doing DC tests, it can never be used in its equivalent test for doing a line leakage. You don't have the same multiplier. If I'm doing an AC test, as an example on a product at 1200 volts, I can pretty well predict what kind of a line leakage current I would have at 120 volts under an open neutral circuit condition based upon the leakage current that I see during the Hipot test when line and neutrals are tied together and I'm testing to any exposed dead metal of the product itself. That would be, I could pretty well predict what kind of a leakage current that I would see as a result of doing a line leakage test on the product. Okay. Why high and low limits? Hipot testers today have multiple failure detection circuits. Years ago, we added the low limit circuit to the tester as a way of verifying that the test was actually being performed on the product. This came about as a result of a visit to one of our customers. We went out to the production area and I witnessed an operator setting up and performing a Hipot test on one of their products, and they Hipot tested the product, and at the same time the tester that they were using did not perform a continuity test. They were doing that as a separate function. It was being done by another operator who happened to be standing on the opposite side of the line, who let out a scream when the Hipot test was conducted on the product. It turned out she was performing a continuity test between two panels on the product at the same time that the Hipot test was going on. Both operators could not see each other because of the size of the product. It was setting on the line and it blocked vision from one side to the other. High voltage was applied to the product, but the return lead was open. So now the product had 1200 volts being applied through the line and neutral conductors. The capacitance of the circuitry to the dead metal allowed for the enclosure of the product to have 1240 volts being applied to the enclosure. The operator doing the continuity test became the return path because she was standing on a concrete floor, or actually leaning up against the conveyor that the product was, pallet was actually setting on. So the product was sitting there isolated and energized at 1240 volts. And the operator met the requirements of a failed product, being that it had to have an audible and visual alarm. She did let out a scream when she got shocked, and the continuity tester went up flying in the air as a result of the shock hazard. And so we knew that there was a problem right away with the product being tested. I don't think that was the intent of the standard requiring an audible and visual alarm. It did not have a manual reset from that standpoint either. Anyway, little humor in that shock hazard, if you can see that from time to time. But anyway, as a result of that, we kind of came back with an idea that, hey, you know what, if we're monitoring not only the high limits, but we set a low limit feature based upon how much current the product would normally draw, if the lead's open, we would know that right away. and shut down the test, and that would eliminate the shock hazard from occurring again. So we built it into our products. We also built in the continuity test function into our products, that it would be doing that test simultaneously. Was a way of eliminating, two potential hazards that, could occur by having a person coming in contact with the item being tested, and also making sure that we were monitoring this function during the testing process. So by having a high and a low limit, you can know right away when a product occurs. It does require you to set the low limit. Okay, if you have the low limit set for 0, it does not help you, okay, because you're going to be drawing more than 0 leakage current during your Hipot test. So, you must set the low limit in order for it to, provide you any benefit in knowing that a test was actually being performed on your product. Okay. So again, this circuit allows you to set up a window of operation to monitor the test. Minimum leakage level is programmed into the Hipot, which must exceed the current seen during the test. Again, this is selected based upon the average current draw of the device under test during the Hipot test. This is done to guarantee that a test was actually performed on the device under test, verifying that there are no open connections in the test circuit, such as an open test lead. So this is the reason for doing a low limit test. One thing, it kind of tells you that your equipment is working also. If you have a low limit set and you initiate a test, if you're not drawing that low limit, it's going to set off the failure alarm. So, it's a way of going through and doing this. Okay, if you're doing a DC test, the low limit function does not work that well. Part of the reason for that is if you are doing a long ramp or a slow ramp on your product, you will see some initial charging current that is occurring. But in many cases, if you're testing something that is not that high of capacitance, if it has a high insulation resistance, you may not see very much leakage current. And it may be below the resolution of the Hipot tester. So one way of guaranteeing that we are performing a test, if you're doing DC, was that we monitor the charging current upon initially applying the voltage. This is what we call our charge low feature. And this was, again, was added for DC applications where in many cases the steady state leakage current would drop down below the resolution of the current meter during the dwell cycle, and it resulted in a false low limit failure. Okay. The low limit circuit is a patented circuit. It monitors the charging current through the device under test during the ramp cycle to verify that the device under test is connected and there are no open circuits, which could be due to an open test lead or an open connection. Okay. The charge low limit should be set for each type of device under test. After the test voltage is selected, after the ramp has been programmed into the test. Okay. So your parameters, if you change any of these parameters, then you have to reset your low limit. If you put in a different type of product that has a different charging current, again, you may have to set up a different low limit. So this is one of the advantages for having multiple memories where you can set up different test scenarios for different types of products. Okay. When the device under test is connected, the charging current is measured when setting up this feature, and it's programmed into the setup file, for that particular product. So, you have to set up a separate, file for each type of product, if you have varying capacitances within the product itself. Okay. If people try to set up a very low value of leakage current in doing a DC test, then we had a problem where in many cases, if you ramped up the voltage too quickly, the charging current would trip off the Hipot tester because you exceeded this low leakage current value. And one way of getting around that is we developed this ramp high circuit that essentially turned off the high limit function or set it to the maximum capacity of the Hipot tester during the ramping function. So it allowed you to more quickly ramp up your test voltage to apply your Hipot test voltage to your device under test, kind of ignoring the trip setting, but once you hit the dwell cycle, then it turned your your high limit trip setting back on to monitor that leakage current throughout the dwell cycle of your Hipot test. So the ramp high feature is helps you ramp up your product at a little bit faster rate, ignoring your high limit setting until you hit the dwell mode. Okay. We talked about these different detection networks. This is kind of shows you some of the, at least three of the separate networks: the arc detector, the leakage detector, and the overload detector. Some of these things operate at different speeds. The arc detector looks at high frequency noise that is generated. So it's what we call a low pass filter. It allows low frequencies to go through and only looks for the high frequency noise that is being generated due to an arcing condition. And it's on a high-speed shutdown, so it will detect a failure within 400 microseconds and shut down the CPU, if it sees an arc occurring. The overload detector is also on a high-speed shutdown. It is a high current detector that is set for the maximum capacity of the instrument itself. So if the overload detector goes off, it's usually because you may have a short circuit or very high initial current flow. You could have a catastrophic failure that occurs due to an arc where the thing flashes over and now the current exceeds the capacity of the instrument. So both of these detectors, the arc detector and the overload detector, may go off simultaneously. If the arc detector goes off by itself, the instrument will display arc failure. If the arc detector and overload detector go off simultaneously, the instrument will display a breakdown. If you have the leakage detector, both the high and the low limits, that's a slower detector. It only samples every 100 milliseconds. It looks at low frequency stuff, DC 50, 60 hertz type stuff scenario, and this will either signal you a high limit failure or a low limit failure. Some of the instruments, basically, if you have a overload, immediately upon applying your test voltage, the instrument will display a short. Again, some of these, if you have an overload and an arc, it will say breakdown. If you just have an overload that has occurred where you've exceeded the maximum capacity of the instrument, but you didn't have an arc that went on, then it would indicate an OFL condition. So the different detectors have, depending upon what signal is being sent into the CPU, will give you a different response. The diagram here shows you a little bit how the arc detector works. If you have an arcing condition that's going on, typically you have the high frequency noise that is being generated at the peaks of the sine waves, and this is the signal that is fed into the high pass filter, and it only looks at the high frequency stuff that is going off, and if it exceeds the value set on the comparator circuit, then through the sensitivity adjustments down here, we have a 1 through 9 setting, which is roughly anywhere from a 2 to a 20 milliamp peak current level, with 9 being the most sensitive level, which would be around a 2 milliamp peak current level. So if this value, if this was set for 9, if this value exceeded a 2 milliamp peak current level, then it would trip off the comparator and send an interrupt into the CPU. If it went off by itself, it would indicate arc. If it went off and you had an avalanche of current that tripped off the overload, then the CPU signal or output would indicate a breakdown on the display of the instrument. This shows a little bit more about the leakage detector. Again, using a window comparator, we are allowed to set up a high limit based upon what your product would normally draw, and a low limit, again, based upon what your product would normally draw. Now, some standards will tell you to set your trip setting at, using a 120 k ohm resistor based upon your test voltage. Some of them will tell you to set your trip point to a specific current level, like 60335 is an example. For a routine production line test, says anywhere from a 5 to a 30 milliamp trip setting. Now that's for household appliances. So it gives you a range from 5 to 30 milliamps is what your normal value would be. Some standards will tell you to set it to something slightly higher than what your product would normally draw. And some will tell you just to use a 120 k ohm value, and your tester must signal a failure within a half a second once you apply the voltage across that 120,000 ohm resistor. The low limit is not specified. That is more of a quality issue that is done from your standpoint to make sure that you are doing a test on your product, and it's also helpful in the again, making sure that you are in fact testing a product each time you go through and do your test. The overload detector, again, is set on the uses fixed hardware set points, a setting that is above the maximum current rating of the tester. It is also on a high-speed shutdown. It will send an interrupt circuit into the CPU. If the overload detector goes off by itself, it will indicate an OFL. If it goes off immediately upon applying your test voltage, typically you will see short registered on the display. If it goes off in conjunction with the arc detector, it will indicate a breakdown on the display of the instrument. Okay. Line and load regulation. Line regulation, basically instruments that did not have a regulated output, where they weren't regulated due to the input voltage, could give you, your output could vary depending upon what was going on with the input voltage. If you set a Hipot up and you set it for 1,000 volts with 115 volt applied to the input, then you had a reading of 1,000 volts each time you did the test. But what happened if your voltage varied during the day? Maybe you had a little bit of a brownout condition where your input voltage dropped down, might have been down anywhere from 108 to 110 volt level. Let's say it was down to 110 volts. What happened to my output voltage? Well, now I might only be putting out a little over 900 volts instead of 1,000 volts. So what happens if you had an audit during this time and they came in and they said, well, we want to witness your test. And now they look at the Hipot tester and the standard says you should be testing at 1,000 volts, but you're only testing at 900, you may have a problem, okay? That value is maybe in excess of what you are allowed to deviate. Some standards will only allow you to have maybe even a 5% variance in your, in your test voltage, and that's a good argument also for. I've had customers say, well, hey, I'm testing products that are both 115 volt and 230 volt input voltage, so my test potential may be different for these two products. Rather than setting up two different test potentials, I may test everything at the 230 volt input voltage level. So instead of maybe doing a 1200 volt test, I'm now doing a 1500 volt test based upon, like, if it were a 230 volt rated product. That is, in some cases, you could be written up as a variance on that for not testing at the proper test potential, even though you are doing a more stringent test. But that can be a problem. I have seen it done by different testing agencies. Had customers contact me about, that particular problem. Hey, it says in the standard it's got to be tested according to the standard. If you vary from that, you may be written up on it. Okay, load regulation. What happens if my load varies? If I'm testing different products, even though it may require a 1,000 volt test, well, depending upon how it is loaded down, the voltage could in fact sag. Back in, I think it was like 1984, if my memory serves me correct, UL came out with a requirement to test the regulation of the Hipot tester. And they started on a bunch of different standards. Back then, UL 544 was one of the standards for medical equipment that was being used. And they specified using a variable load ranging from, on a low end, 120 k ohm, on a high end, I think it was 2.148 megohms. And it had like 10 different values of resistors that you could use this load box for testing the regulation of your Hipot tester. And so you would set your Hipot tester for a particular voltage, and let's say it was 1,000 volts, and then you would connect it to these different resistor values and monitor what was going on with the voltage. As long as your voltage did not sag, you were fine. If it tripped off before you got down to 120K, that was acceptable also. But by the time you got down to 120K, then your Hipot tester had to indicate a failure within a half a second. But, you know, you had to test the regulation of the Hipot tester. If it sagged, then you could increase your test potential to a value that was in fact higher than your 1,000 volt, just to make sure that whenever I got to my trip setting, I was not below the 1,000 volt level. Okay, I must maintain that minimum value, because what that allowed me to do was actually set this voltage where it was actually a little higher, you know, at you know, different varying load conditions and stuff, as long as it did not drop below the 1,000 volt potential to the point where you know, I generated a failure. Okay, some of the safety features that have been added, a GFI circuit. I think everybody knows what a standard household GFI does. It looks for an imbalance of current flowing between the line and the neutral circuit, and it figures if for some reason this current is not the same, it's taking an alternate source back to the supply through ground. That alternate source could be a person. So if you know, a standard household GFI, if you see somewhere in around 5 milliamps of leakage current flowing through that circuit, it will then shut off that breaker that could be supplying anywhere up to maybe 15, 20 amps of current, you know, through your, you know, the device that the product is actually operating. Our smart GFI works something very like that. We're monitoring the current that is flowing through the circuit, and we're also monitoring the current going to ground. And if the current exceeds our 450 microamp threshold that we set for our smart GFI, then it will shut down the Hipot tester. Why did we pick such a low value? Since we're dealing with high voltage, we wanted to set the ground sense circuit to something that it was really closer to your perception level. Okay, so our GFI circuit is normally set for about 450 microamps. You know, okay, so that basically is our, you know, our threshold for our ground sense circuit. We have had customers request that we adjust this, you know, so that it has been done as an option where we've increased that. You know, we give you the option of turning it on or off. We realize if you are testing something that is tied back to earth ground, you don't want it where it's always going to give you a false failure where, you know, you're going to trip off the GFI. So you can turn it on or off. If you ground the return of your product, it automatically disables the smart GFI. But you also do have a setting where you can turn it on or off. This is what makes the thing smart. Okay. It can give you some nuisance tripping if you are testing something that is, if you're testing two isolated circuits and you have a leakage path to earth. If that leakage path to earth exceeds 450 microamps, it can give you a false GFI. So in that case, you may have to disable it or request an option to change the GFI setting. This is a hardware setting within the instrument itself right now. Okay. Okay, ground continuity. The Hipot testers today have a ground continuity circuit built into them. If you're testing a product that has a 3-prong plug on it, doing a routine production line test, you may have to test your product, test the ground circuit to make sure that it does have continuity. Some of the standards say you can use any indicating device, battery, buzzer, the like, to determine compliance to that. The problem with that is these type of devices are, you don't really know what they're set, how much resistance does it require before the bulb no longer lights up. I did some testing on some of these pen light type things, and I found out that it's normally somewhere around 8 ohms of resistance and the light will no longer light. Is that a good ground? Unfortunately, most of your standards do not specify that. Some standards are now specifying a maximum resistance of your ground continuity circuit. So as some of these standards are being rewritten, some of them are specifying, and what is that number coming out to? In many cases, it's 0.1 ohms as far as the maximum resistance of that ground circuit. Most of our standard instruments have a 1 ohm maximum continuity. That is what we used to use. Some of our testers now have an adjustable continuity function where you can set it to a all the way down to 0.1 ohms, or even increase that circuit. So the continuity function is important. Again, if you are testing a product that is terminated in a 3-prong plug. Okay. Again, your instruments today have remote I/O functions. You can utilize a programmable logic controller to control the Hipot tester, sending test commands, selecting different memories, resetting the Hipot tester. Some of the old remote I/O functions. We had a 10-volt analog circuit that we used in some of our older instruments. We still offer that on some of the Hipot Ultras. Some of the higher levels of automation today, we have either RS-232, IEEE, Ethernet interfaces available on our testers to allow you to interface this with a computer. Some of the testers, we have a CAM software package that we offer with our instruments. Others, you may want to write your own commands. Some of the stuff we use, LabVIEW drivers in some cases, depending upon the equipment, to control the equipment and stuff also. So there are a lot of different ways of setting up, performing a test. The equipment, one of the most important features and stuff that I think we have with our equipment also is a remote interlock that will allow you to connect your Hipot to an enclosure to guard the device being tested. If you can't come in contact with high voltage, then the operator is not going to get shocked. So if you have an enclosure for your product, or maybe even utilizing a light curtain in your testing process that makes sure that the operator cannot come in contact with the device under test, then it eliminates the shock hazard. Today, OSHA is becoming much more stringent on testing requirements and personal protection equipment. Years ago, it wasn't, you never seen anybody doing testing in a production line using high voltage gloves. Today, if you have an OSHA inspection and you have exposed energized circuits, and the operator can get shocked as a result of coming in contact with that exposed energized circuit, you can be held liable. You must provide personal protection equipment to protect the operator. So either you guard the product being tested, or you provide them personal protective equipment. And the problem with some of the PPE, it is, it's not the most convenient stuff to work in. Trying to handle a product, it requires that you test the personal protection equipment and make sure that it is compliant to agency standards. They must be visually inspected before each use and electrically tested at least every 6 months, I think. Just to make sure that they are in fact safe. So the interlock circuit is an important feature to setting up your product so it is safe, where the operator cannot receive an electrical shock as a result of going through and doing your testing process. Okay. With that, I'm going to leave it open for a couple more minutes just to see if we do have any questions. I ran a little bit over on my time, but if you'd like a copy of this presentation, again, you can either email Rebecca or Jim Kennedy at asresearch.com, and or even send an email to info@asresearch.com, and we'll get that out to you. If you have any questions that we did not get to during the presentation that may have come across, again, you can send us an email, info@asresearch.com, and we'll do our best to get back to you as quickly as possible and provide you with an answer and stuff on that. The presentation today has been recorded, and it will be available probably within the next couple of days on our website. Our website is listed here below, asresearch.com, and if you go under events and training, you can see all of our webinars, our schedule, as well as the webinars that have been archived. Okay. With that, I have not seen any additional questions that have come across. I thank everyone for attending, and please, look at our webinar schedule and, join us on our next webinar. Thank you.